Hello and welcome again to the deep learning course. Today we'll be working with the transfer learning in the convolution neural network. So without further ado, let's get started. Previously, in the previous lecture, we have built a model from scratch. Basically, it holding two convolutional neural network with real-one max pooling inside each of which. And this will be taking this image after some pre-processing that we have converted into grayscale. And after this convolution block, which is main objective to extract the most important features, the such output or the most extracted features are being inserted to the linear blocks, and after which we apply any softmax or probability matrix, probability function to give the final output. So basically, training such CNN block is expensive somehow. And the approaches that we have discussed through the CNN intro theory lecture with these large models that have been trained on thousands and thousands of data, and they have producing high accuracy on the AlexNet data, as you have mentioned before. So in that case, the point here is to use the weights of these trained models and insert them into our custom model in order to benefit from all of its learning by taking its weights. Like, we are going to assume that such weights are going to be trained enough and made sure that they are going to help us in predicting the correct label quickly without many epochs to train the model. So in order to reduce the number of epochs to train such a model from scratch with all these random weights being initialized, we will be replacing it with an already learned model, like a pre-trained model, which will be transferring the learning of such model into our custom model. So let's discuss, like, for example, here, this is the Resnet model, for example, and it consists of many layers. So basically, we will be focusing most on the early layers because they are going to be more general than the final layers. Because the final layers are more focused on fine-tuned to be predicting the final label. Okay, and the final label is different from our label, so in that case we don't care about the final layers, but the initial layers, like for example these ones, that we are caring about because they actually, the main objective of them is to extract the information from the image regardless of what is the downstream task. So I'm just working to extract them. So basically we will be cutting this Resnet model into into two pieces, for example, and we will be taking this first top layer and freeze them. We will not be training this, okay, because this will be more larger than our custom model, so it will take much more training. Although, like, it can be a little bit, maybe can be fine-tuned a little bit, but by the end of the day we might be should be freezing these already trained layers and already dropping these external or final layers, and only insert these models into our custom model. Okay, so instead of training all the model from scratch, we will be using an already trained model, which is being the Resnet, the DenseNet, the AlexNet anyway. So you can choose as much as you can from this TorchVision models package. You can check this package and choose what you need. Okay, and insert it from here. I will, here in this tutorial, will be teaching you how to crop this model and only consider a subset of the layers, not all of them. So let's get started. Here I'll be importing this final import here that is added from the last lecture. This is the model TorchVision.model, which will hold all the TorchVision, the CNN convolutional neural network models. So in that case, we can work on this CIFAR10 data as well. It has this, I have already downloaded it Okay, if you need, you might be seeing as a progress bar, and it contains like 50K for training and 10K for testing, and already have 3 channels. And a point here that we need to know that we cannot apply the grayscale transformation on the images as we have done before, because basically these images are in the 3 channel red, green, blue, and the Resnet also accepts a model, accepts images with red, green, blue. So in that case, you need to confirm that your input have the same number of channels of this model. Okay, so if you trained on any model, you need to make sure that what is the input and what is the output, because you need to apply some linear blocks after it. Okay, so here I'm just checking that if the targets are biased or not, and here I'm plotting some of these images. And after this, let's start by, for example, using the Resnet model. So let's start with this models dot, and it will be producing all of these models that you can use. Okay, this is the Inception model, the Google Net, and this is the MassNet, the mobile net. All of the models, or also updated models we can use. I will just focus on the Resnet, maybe Resnet 50, for example, Redis 34 and 18, 152. So you can use any. I'll just try this one, and I'll set the pre-train to be true, because I need the pre-trained weight also to be downloaded by this. Okay, so I can call it ResNet. I'm just showing you how you can use it, but then we will be inserting it into our model. Like for example, you have already built this, and this is our model. So basically we will be removing this part. This block will be dropped and will be replaced by the ResNet. Okay, so that's the main change that we are going to do. Okay, so let's continue now with our playground part. So just working on with our ResNet, and here it is already downloaded. If you can print it, it will be showing you these sequential layers, and final layers is the FC, and it produces an output of 2048, and the output is 1000 class. So that's the last layers that we can drop. Also, you can check how many layers with checking the children of it and length of it. Okay, I think I need to apply list before it. Okay, so you see you have 10 layers within this ResNet, and it's not explicitly layers, but they are a block of layers. Okay, as you have already noticed while printing, like this whole block is considered a single layer, so they are a sub sequence of blocks. Okay, like convolution, batch normalization, and then convolution again, batch again. Okay, so then we down sampling. Okay, so you can check also the all the codes, and so it is being published through repo. There is net repo. Anyway, so I will just be using like the last layers, but except the last layer, for example. So I need to use this fully connected layer, and I need all of these 9 layers. So I can check this. Okay, so here I use 9 layers. So this would basically will be not the layer, it should be my model. So that's the embedding model. I can call it the embedding model for better understanding. Okay, so the embedding model is nothing but to extract our main features from. Okay, so after this we should be inserting to it some images. I will just try this image batch. So for example, I will take it from the CIFAR. So CIFAR train.data. I take the first 10 batch. So as you can see here, this is the dimension of the original data. I can call it, I can first convert it to a tensor. Okay, and I call it image batch. Okay, so now it's a tensor and we have these three channels. So let's try to pass these to the embedding model and take a look what is the output. Okay, so it is calling me like list is not callable. So basically we need first not to just make it in a list format. We need to also convert it into a PyTorch sequential class, which takes this embedding model. And as you know, like this sequential class that we have already applied through our model, like we're building a sequential layer sub pipeline of convolutional blocks here. So it doesn't take a list, so it takes only the content of the list, okay, without explicitly putting them into a list. Okay, so we need also to pass the content of these layers, which is also a list. So we pass this in a sequential part like this. And here, this is our embedding model layers that we can or normally pass into it images. So let's start now. And here we are saying that expected input is 10, 32, 32 by 3 to have 3 channels, but got 32 channels. So from this error, we can understand like this the acceptable number of channels through this model is 3, and actually it accepted this channel to be in this index, and it found 32. So it cannot accept 32. So we need to reshape this tensor as well. So let's reshape it first, and then it will be 10 by 3 by 32 by 32. Okay, so now let's check the shape. Okay, it's now in the correct format, and now let's produce the output. Okay, it needs to be a float. This will be done through the pre-processing, so we need to convert it to float. And finally, we have the predictions. Not the predictions actually, but the flattened tensor. It's the final of all the Resnet layers. Okay, so for example, this is extract features. We can call it features and check its shape. So basically, it is 10 by 20K, 48, and 1 by 1. So that's what we need to do with what we need to pass through the linear layer. So basically, this is the extracted feature from the pre-trained model. We need to pass now to our linear blocks and go within our original model. Okay. So, but before this, we need to also remove any gradient from our Resnet. We need to freeze them. So for example, here, through this Resnet, I can check its parameters. And for example, it will be a method, and I would be for param in such. I can just show you what is this param, or okay, so basically, as you can see, it's a tensor and it requires a gradient. Okay, so this required gradient equal set to true means that this model will be trainable. So these parameters, all the Resnet model now will be trained. And how we can freeze it, because this node is our target to train the Resnet or to fine tune as at least, but we need only also to remove this required grads to be false. Okay. So now let's check it again. Now it is removed. Okay. So we will be passing across all these Resnet parameters and set the gradient to be false. So in that case, we'll be freezing the model, that the Resnet model or any model that we can use. Okay. So let's now bring these components into our original model and see how it can be used. So let's get started. Now I'll be combining them all in a single cell in order to copy paste them easily. Okay, so that's pretty much what our input extracting features module. So first will be inserting them to this, and here is the Resnet, and we'll be freezing the pre-trained model parameters, and then we'll be using all of its layers except its last layer. You can also use as much as you can, like you can use only the 4 layers, like for example this only, I need only the 4 layers, so you can have this as much as you can and flatten this input. Like for example, if I use first 4 only layers and check it, I just want to show you. If I check only the first 4 layers, okay, and then I pass this to the model. So as you can see here, it breaks out to 10 and 64 by 8 by 8. So you need to as well apply this torch dot flatten this feature, okay, and it will be yeah, so it will be multiplying all these into the same, like it will be 64 by 8 by 8, and this will be 4096, and you can pass this 4096 to the linear input. Okay, so I just showing you how you can flexibly use any layers, any hidden layers that you can. Okay, maybe like this previous layer is hard dimension because it's a convolution. Actually, we have a breakdown in a convolution layer, while this last one, if you have done this last one, so it will be after all the convolution have been done, and we need to flatten them into a single dimension. Okay, so as you remember, was 2048. This the final number. I'll just show you again. Yeah, this is all. So this is the main number that we need to use into our linear block as an input instead of all of these. Okay, I just insert it as here, and I can now remove it. This model is extracting. Okay. And then I can work on it instead of this conv block and just it. Okay, and this can be also reshaped or flattened as the same thing. And then we can run our model safely. Let's try with a batch. Okay, we need to also convert them to a float. Okay, so as you can see here, this is the final shape of our model. This 10 classes, and this the batch size is 10. So we need also to apply argmax. We can work on, as you can see here, the numbers have been different from this random initialization, but also through the training you can find out how these parameters, how this using this transfer learning model can be optimizing or making our training loop is much efficient and reducing the execution time with using these pre-trained models. I hope you understand, and you can try on your own other models as well. And let me know in the comments how is the accuracy being improved. Thank you, and see you then. Thank you.